Okay. We're going to get into torque in a little bit. We're going to do torque. Okay. But I'm going to give you guys another problem. To work on friction. Okay, is that cool? Because we've done pulleys and forces and friction, right? Okay.
Pulleys is a sub
component of that, yeah. Mm-hmm. Okay. At the end of the class, I'm going to start talking about torque. So I sort of briefly introduced that at the beginning of yesterday's class, of this morning's class. So what's today? Is today Thursday? No, Wednesday. Okay. So tomorrow I'm gonna get. Listen. Tomorrow I'm gonna get into torque. Actually, you know what? I'm gonna get into torque right now. That's what I'm gonna do.
Yeah, you are.
Because the other class is gonna have to look at the YouTube video and get caught up that way. I gotta get everyone on page. All right. We're gonna talk about torque today. That's what we're gonna do. O-R-Q-E-E. Q-U-E. Is that what I said? No. Torque. Hey guys, quiet. Okay. So, hey guys, I'm serious. Stop. Okay. So, does anyone know what torque is?
It's when you twist.
Okay. That's the twerking.
No.
It's
I can demonstrate torque.
No, that's quite all right.
No, tomorrow you can.
But okay. Torque. What about torque? What is torque, guys?
It's a force.
What kind of force?
It's a twisting force.
Beautifully defined. It is a twisting.
Wow. I was like,
What the heck?
She answers the questions. You guys can all answer the questions. I do email Lauren the questions ahead of time. All right. So, torque is a twisting force. All right. It takes a certain amount of twisting force to open and close a container, like a jar of peanut butter. Okay. It's a twisting force. Okay. Shh, quiet. Listen up. Listen up, guys. Guys, I am moving forward whether you listen to me or not. And you will be responsible for the material.
No, he will, Hannah, because I want to make him.
Torque is defined as force times the length that the force is applied to, perpendicular to that.
Is that like a cursive T?
Yeah, it's another T that I'm trying to not use as another T for time, and it's F times L perpendicular. And what I mean is this: if I have a bar or a beam, and it's pivoting around this point, and I have a force pulling on that beam at a distance L, and this is my force, the force is perpendicular to the length that I'm acting on from the pivot point. Do you guys see that? Okay. That would be different than if I had my beam, same pivot point, same beam, and I was acting in a force this direction. That is not perpendicular to this length L. Right? This force is not perpendicular. Doesn't mean you can't solve it, and we'll talk a little bit about how to do that. But when we talk about torque, we're talking about length times the force perpendicular. Okay? Everyone got that? Okay. So, a simple example that you guys have all probably used when you were kids, or maybe they've outlawed them now for whatever reason.
Need for speed.
What?
You can increase the horsepower in the torque.
Okay. Yes. But torque in an automobile is a little more convoluted than what we're going to be getting into. It is really torque, but you have to go through a few steps to get to the actual torque value.
Yeah.
This is what kind of thing? What kind of thing am I drawing here? What? Yeah, it's like a seesaw, right? You got a handle. Okay. All right. So we're going to have some individual another individual hanging out in the seesaw, right? Okay. If they're of equal weight, how far away from the pivot point should they be?
Same.
If they want to balance.
Same.
Same distance. So, if I have my length, L1, and my length, L2, and I have a force of gravity for 1 and a force of gravity for 2, okay, I can actually sum up these torques. And I can say there's a torque for 1 and there's a torque for 2. And I can actually sum up the torques. I'm going to call this point A, point B, and point C. So the torques around A are going to equal my torque 1 plus my torque 2. And if I have one torque, if I go back and I have the one torque, I've got the one beam, and I have a force on it, what's it going to want to do? If I have the one beam, I've got an L and I've got a force, what's it going to want to do? It's going to want to twist around that point, right?
Yes.
Everyone with me?
Yes.
Yeah.
Hannah? If I have a beam and I have a force and a length from the pivot point, it's going to want to twist that beam, right? It's going to rotate right here, around this point right there. This bar, if I take a bar and I turn it, it's like a door handle, it's going to want to pivot, right? Okay. The only thing from stopping it from, yeah, I'm just saying, let's say I had a thing, a bar, it's going to want to twist. In this scenario, if I only had one guy and the other guy wasn't there, it would want to swing down. To balance out, I'm going to have to sum the torques up. And if it's balancing, what's the net torque? 0. Then that torque is 0. Yes, ma'am.
So where do you get T1 and T2?
The torque that is generated by force 1 is T1, and the torque generated by force 2 is T2.
So it's not like a line. It's just like
It's a twisting. What do you mean it's not like a line?
like you wouldn't draw like force 1 is like a line, drawing like up or down. Is T1 like a line?
It's actually, so here would be, so T1 would be, a twisting force that way, and this would be called T2. So it's really drawn like a circle, okay, an arc. There's that torque. These torques have to be balanced. Now, if they sum up to be 0, that means one torque is positive and the other torque is negative. So let's determine how we figure that out. So we know that we talked about torque a moment ago, that torque was equal to what? Someone look back at your notes.
F times L perpendicular.
Perpendicular.
What does F and L stand for?
Force and length. Okay? So if I look at torque 1 is F1 times L1 plus F2 times L2, and that's going to equal 0. Does that make sense? Okay. Let's assume for the moment that F1 equals F2 and they all equal 5 newtons. Let's also assume that L1 equals L2 and it equals 2 meters. Does that make sense? And now let's apply the signs. So force 1, what direction is force 1 going? Down. Okay? So that force 1 value is going to be what? Negative what? Negative 5 newtons. The length of 1 is how long? How long is L1? And how long is it?
2 meters.
L1 equals L2, which equals
So 1 meter.
2 meters. Each L is 2 meters. Okay? Here's the thing, though. If I'm taking this torque, obviously I'm taking the torque, I'm not taking it around A, I'm taking it around point B, the center pivot point, right? If I'm taking the torque around point B, that means there's my pivot point. L1 is to the left or the right of the pivot point? To the left. Therefore, if my length goes from the pivot point left, that length is negative. So it's negative 5 newtons times a negative 2 meters. Plus, what's the direction of force 2? Negative. So what's the value of force 2? Negative 5 meters. Oops. You're right.
Oh, wait.
Negative 5 newtons times 2 meters. Now, if L1 was negative because it was left of the pivot point, L2 is to the right of the pivot point, what should it be? Positive. So times 2 meters. So that means I'm going to get positive 10 Newton meters, that's the unit of torque, plus a negative 10 Newton meters, and that does in fact equal 0. Does that make sense?
Wait, why is it? He told us.
I just gave you some values. I gave you some values. Yes, FG1. I'm sorry. Yeah, FG2.
But if why are they both negative? I don't understand. Like,
What? Hold on, Carmen. What is they?
Oh, so not
Forces. What direction are the forces?
down.
Down. So we always say that any force going down is
Negative.
negative. Got it? Okay. The issue is this. When you're doing the sum of the torques, this is important. Okay? If that's my pivot point, here's my pivot point, PP, pivot point. Any length to the right is going to be, positive. Any length to the left is going to be negative. You guys see it? Girls, there's too much conversation. I am talking about something extremely critical that you're going to mess up. There's too much conversation. Listen. I understand, but I'm literally going through this, and there's too much conversation. Wait for that conversation until I get through. So I'm trying to tell you. The length to the left of the pivot point is always going to be what sign? The length to the right of the pivot point is going to be what sign? Positive. And by the way, the pivot point's not always going to be in the middle, and I'll talk about that in a minute. Okay. Does everyone see this? Everyone get this? So in this case, my torques are balanced. So that means and I'm going to call them, let's just call them F1 for the moment. F1 times L1 equals F2 times L2, right?
Yes.
To be balanced. If I increase my force 1, that increases all of that torque. To make it balanced, I have to increase one of the two things. I can either increase the force or the length. Okay? Here's a great daily example of torque that you guys go through every day.
Open and close.
Okay. I'm going to push there's a certain amount of force. In your mind, you say force, but in reality, it's torque. A certain amount of torque that I have to push to overcome this spring in the way of the door to make it twist open. Right? Without this spring, the door would just stay open. I'm fighting that spring. Okay? Where is it easiest to push on the door to open it?
The farthest away from
Out here, right? They don't ever put the door handles here, right? Because it's much harder to push. Well, let's think about it. If the amount of torque to open that door is fixed, and I have a certain fixed amount of force, right, that I can give, where I'm measuring my force, I have a longer length, I require less force to make that torque. I have a shorter length, I'm going to require to have more force to get to that same torque. Does that make sense? You guys with me? It's an important concept. Notice, the spring is pushing on the door at a point. This distance from the pivot point, which is my hinge. So it's going to have to always push at a certain force, and it will always push at a specific force. I have to push at another length. Does that make sense? It's just like a seesaw, except the pivot point's not in the middle, the pivot point's at the end. Do you guys see that? So I'm actually pushing in two directions on one bar. Yes, ma'am?
Isn't the hinge
The hinge is that's right. The hinge is the pivot point on the door. Whereas in this case, the pivot point is the middle of the seesaw.
I have a question. Would it be okay if I took one of your soldering irons?
Yeah, you can take the non-Weller one. You can take the cheapy one,
The red one.
the red one.
Okay.
But it's not the greatest thing. Take some copper steel wool and clean it,
Okay.
and that way you have a nice clean surface.
Okay.
You may go crazy trying to solder with that.
Okay. Because I have to leave early today, so I'm not going to get any more.
Yeah. Okay. All right, and I will let you borrow it, but it's my only Weller, and I think I may need to use it later today. I mean, my Weller one, the Weller that I can't let you. I may need, the blue one. I may need to keep that.
I'll take the red one.
Yeah, the little handle. Yeah. Okay. Everyone with me so far?
Absolutely.
Okay. So let's look at the door for a second. Let's look at the door. Okay. Here's the door example. Here's my door. Okay. And I'm for simplicity's sake, I'm going to put the hinge right here. We're looking down on the door. We're looking down on the door. Okay, here's my door handle. Okay, everyone there? Right? It's going to rotate this direction. Make sense? Hmm? Okay. All right. So let's look at this for a second. Difference in the scenario is this. Difference in the seesaw is this. I have my pivot point here, and I'm going to have a force from the spring. A force from the spring pulling downward at a certain length. Right? I'm going to call this length LS for length of the spring. Everyone, in that box is a big spring. Okay? I'm also going to have the force of me pushing on the door at another distance. That's going to be L push.
So from the hinge.
From the hinge. Okay, do you guys see that? Because I'm choosing to go from the hinge.
What is that first force?
What is that first force?
The
FS.
F of the spring and L of the spring.
Wait, is that L force or LP?
Wait, there's something in
Oh, wait.
Whoa, whoa, whoa.
Wait, where is
Okay, stop. I'm using F for force, S for spring, L for length, and P for push.
So is FP on the bottom by the table? That's FP.
For pushing, right? And the length of that push, LP. The force of the spring, Fs, and Ls, which is the length of the spring, the length of the distance from where the spring is pushing. Does that make sense? These forces are all perpendicular to the length. Okay? Make sense? All right, now, let's do the sum of, yes?
What if it's not perpendicular?
We may or may not, we probably will not get into this point.
Okay.
But and you guys don't have to listen to this. I'm gonna take 2 minutes to explain it to you. I won't hold you responsible. Canon. If my bar is here, here's my pivot point, and here's my force F. Here's my L. You see that?
Yeah.
Okay. If I want to know the force perpendicular to that length, okay, I can do one of two things. There's a component of that force perpendicular, which is here, that's going to be less than F. And it's going to be that F perpendicular times L. Or, what's easier and I think more conceptually simple, you take this force, bring it down, bring this L over, and it's this force, the original force, times Lx, meaning the x component. Because that's a right triangle, isn't it?
Yeah.
That's theta, and you can determine Lx. If you know L, you can determine Lx. So it's force times the x component. It's a little bit less. Does that make sense? Okay. All right, now, so let's sum up the torques. Phones away. Give me my candy back. Exactly, right? Okay. So, I want it back.
You know what? They're jealous.
Guys, you should never get candy.
They're green with it. I'm so jealous.
All right. So, let's sum the torques. Let's sum the torques. Sum of the torques, and I'm going to call this point A. I'm going to call this point B, and I'm going to call this point C. A is the pivot point, B is force of the spring, C is the distance is the point at which the pushing is happening. Okay? So the torque is going to equal, I have two torques. What are my two torques? The torque due to what? Okay, so I say sum of the torques is the torque due to my spring plus the torque due to what? The push.
So we're not doing FBDs anymore.
We will. We're gonna because you can do this as an FBD. Okay, I'm just trying to give you conceptually. We'll talk about FBDs in a minute. Okay, so give me 1 minute. You can break this down to an FBD. Let me talk about that really briefly. If I'm going to draw an FBD of this, it's simply a line. It's simply a line, and I'm going to have FS, FP, with my pivot point here. Okay. And we'll talk about this in a minute. We'll do an example back with the seesaw with this because I'm going to talk to you about something interesting here. Okay, I'm just trying to get the basic concept of sum of torques. Okay, so if these two torques, right, if they're balanced, let's say I'm pushing on the door isn't moving. I push the door, but it's not going to move, right? So I've started to open the door, and I'm pushing, and now I'm balancing. If I let it go, what's going to happen? Door's going to close. I got to push enough to keep it balanced, right? Because the spring's going to close it. God, I hate that noise. Okay. And when I go to La Jolla, I'm going to remove every spring from every door that I have to deal with. Because I hate the springs. I should remove that spring. The new teachers. Huh? Stop wasting my tape.
Look at her. Put it on her nose.
She got her nose made herself put in tape.
Hannah?
No, it's really
Listen, girls,
Hannah.
put the tape away. You realize guys, shh, listen to me. You realize there's only one approved use of tape on student bodies, right? It's over the mouth. Oh. All right, see?
It needs to be permanently
That's tape on here.
That is pretty funny. Really great.
You can get wrinkled.
I bet if you was your mom on it,
Okay, are we done?
you just gotta learn how to
All right, Hannah, are you done? Good, thank you. All right, so it was actually really funny. I'm laughing on the inside, Hannah. Okay, so if my torques are balanced, what's the total amount of torque that I have? 0. Okay, let's break it down. What's the torque? How do I break down the torque from my spring? What is it equal to? Times? No, times LS. The torque is F times L.
Oh my god.
Times LS. Plus the force of? Guys? Force of the push times the L of the push. Guys, torque, I just said it. Torque equals force times length perpendicular. Thank you, Greg, for paying attention. Okay.
You just need to give it at the end of class because then people are going to complain.
All right. So that is going to equal 0. Listen up. Look over here, please. Look over here. Okay. Let's look at this. All right. Let's assume that our force push is, let's say we're trying to figure out the force push. Actually, no, let's do this. I know how much force I'm pushing, but I don't know how much the spring has to push. Let's assume that I'm pushing at 5 newtons. I want to figure out what the spring force push is. Yes, ma'am?
Okay, so this is assuming it's 0.
Hmm?
Like the overall, like the door's not moving. Like,
Assume that I'm holding the door still. Because if I let the door go, it'll slam closed and annoy Mr. A.
acceleration, right?
Huh?
It'll have an acceleration.
When I let it go,
So,
yeah.
Are you gonna do problems like that?
We may. Let's see how far we get. Right now I'm battling time, okay? And there's certain things I want to get to light too, actually. Okay. No. Don't panic. Shh. Listen up, quiet. God, we haven't gotten into energy. We haven't gotten into potential kinetic energy.
A lot of energy. Sure, but you already said that we're ahead, so.
No, as a whole, I'm a little behind. There's a clock. All right. So I'm trying to figure out how much force the spring is pushing, and we can, because I can measure how much I'm going to push in the door. I can measure the distance I'm going to go to the door, and the distance of the spring. Let's do this, okay? So I'm going to look at this door. This door is roughly. The door is roughly about 0.9 meters. Okay. So. The length of my push is about 0.9 meters. Okay?
Can we actually measure the push like in the
Yeah, the spring force. Yeah. So we're gonna want. So here's where the spring is. The spring is pushing at this point. That point is about 0.25 meters. So the length of the spring is equal to 0.25 meters. Now, let's think about how much force I actually have to push. Let's measure it. Let's measure the actual force. Alright, so I have some measurement.
Oh, can we measure?
Yeah, measure.
No, look.
You can go to a Montessori school. It's interactive.
Okay, here. Alright. Open the door. I want you to.
I've never seen a video guy like that.
So what we're gonna do is, once you guys can see this.
Thank you.
And
Okay, so come here. Come see this.
No, thank you.
I'll take a hard pass.
Now she's holding the door steady, and we've got 3. So each of these is equal, right? So there's 3 forces going on here. Each of these is about 5.5 newtons. So that's enough for the upper. Where's it? So it's 17.5 newtons. Okay? So the force, we were way off. My guess of 5 newtons was way off. It's 17, we measured it 17.5 newtons. Okay? It's 17.5 newtons. Shh. To actually hold that door open. Okay? So we measured that. And now we can determine the amount of force, thank you, that the spring is actually pushing on the door, can't we? So let's do this. Let's put this in here, okay? So the force of the spring is what we're looking for. We don't know that, right? So Fs. What's the length of LS? 0.25. But what direction is it?
Positive.
Negative. So negative 0.25 meters. Right? Plus, what's my pull force or push force? 17.5 newtons. Well, assuming in this orientation my spring force is going to be negative, my push force is a positive or negative?
Wait, we changed it.
No.
What the heck? Yeah, we did.
It was fine. Yeah, but we accurately.
Because we measured it. I told you we measured it. We measured it.
Oh,
Right?
Idiot.
Yes. So is it positive 17 and a half or is it positive or negative 17 and a half? Look at this
Positive.
positive because it's going up. Okay? Times the length. What's the length?
0.9.
Okay, but what direction is it from the pivot point? Left, so it's negative times negative 0.9 meters.
Wait, are we pulling or pushing it?
We pull, but the same as we push, because I only have pull springs. So the pull force to pull it with the springs is the same as the amount we'd have to push. So we're going in that same direction. We're going upward. We're pushing.
Wait, so 0.9 is going this way?
0.9 is going that direction.
Well, then it's positive.
Yeah, it's positive. No. Hold on. The force is 17.5. That's positive. The
Okay.
0.9 is the length.
Okay.
If it's to the left of anything to the left of the
Okay,
pivot
okay.
point, it's going to be negative. Anything to the right of the pivot point is going to be positive.
Got it.
It really is arbitrary, but we want to be consistent. Okay? Okay. So that means it's negative 0.25 Fs plus 0.9 times 17.5. So it's actually minus because it's negative. Minus that 1575. Minus 15.75. Right? Newton meters. Do you guys see why it's Newton meters?
Is that torque or no?
That's the torque. That's a torque value. That's a torque value that we're applying. 15.75 Newton meters.
So does torque have its own like measurement or no?
I can't hear you.
Is it just Newton meters?
It's Newton meters. Torque is in Newton meters, a force times a length. There's no other torque unit besides. You could have inch pounds, meter pounds, Newton meters. Okay. Yes, ma'am.
So isn't it equal to 0?
Okay. It's going to equal 0 because we're balanced. Now we have one equation, one unknown. So the spring is going to be equal to 15.75. Okay, it's positive, divided by a negative 0.25. So we're actually having to put 63 newtons of force. Negative 63 newtons of force on that door, on that spring. That's a lot of force. That is, if you pulled 17, think about this. It's 63 divided by 17. Okay, it's about 3, it's like 3 times the amount. Okay? It's like 3 people pushing against you. Okay?
I can handle it.
All right. So if you were having to push at that point, you'd have to have 3 of you pushing the same amount. Okay? Does that make sense?
Yeah.
Does this make sense where we are, guys?
Yeah.
Okay. All right. I'm gonna do this. You guys are ahead. I'm gonna let this go for the moment. I'm gonna catch the group up. All right. Shoot.